This is Chapter 14, Glaciers, Shorelines, and Changing Sea Levels, Lecture 2. Picking up now with how changes in the Earth's tilt may influence global glaciations. Okay, so we actually call these Milankovitch cycles. There's things that are happening on a planetary scale that affect our climate and make it colder or warmer. So the Earth's rotational axis, it's tilted compared to the plane of orbit around the sun. And this angle changes over tens of thousands of years. So we have to think about how more or less tilt might affect how different the seasons are, summer versus winter, or would be. Uh, so we're seeing a few different angles on our axis of rotation. More tilt on the left. Our present tilt is, say, 23.5 degrees, and then less tilt. Our winter temperature is less important here. At maximum tilt, our warmer summers are near the poles. We have more melting and less glaciation. We're in the middle right now, I guess, in this data set. Our present day tilt is adjusting back from maximum. And then our minimum tilt, you're going to have cooler summers, less melting, and more glaciers. So we're kind of in the middle here. Should stabilize our glaciers, but there's more factors than just the tilt of the Earth that are affecting our climate right now. So we also have another thing that affects our climate. It's the wobble of our rotational axis. We call that precession. It could be kind of a minor factor, I'm not sure. Or the shape of the orbit, the eccentricity, can influence our global climate. Let's think about what factors that could influence solar heating of the Earth and glacial episodes. Okay, so this scene has volcanic ash from a volcanic eruption, glacial ice, clouds, and the sun, of course. We could have a change in solar output, say an increase in sunspot activity interpreted to be accompanied by an increase in solar output, so more heat. We could have an increase in reflectivity, we call that albedo, from snow or clouds, causing cooling. And we could have from this volcanic eruption a release of greenhouse gases by volcanoes to trap more heat. Volcanic ash and dust also reflect solar radiation back into space, causing cooling. There's also the role of ocean currents to consider and the continental position. So where are the continents? Right now, this is the north, this is the south. So we've got our ice at the north and the south. If our continent is mostly at the equator, it's going to be warmer and it's not going to glaciate. Cold ocean currents help cool the land, allowing glaciers to form if there is sufficient precipitation. So it's not just elevation and precipitation alone, it's also the ocean playing a part. Sometimes cold currents can inhibit growth because they put less moisture into the atmosphere, so you have less precipitation. All right, and then warm currents, those can warm adjacent parts of a continent, inhibiting glaciation. All right. We'll sort of pause on glaciers for now. It'll come back. But let's think about shorelines. Okay, so we'll observe the processes here that affect shorelines. You have offshore currents, waves generated from wind. They can move sediment and erode and deposit material. You can have a river delivering sediment to the shoreline, and then coarser materials are deposited closer to the shoreline as a delta, like the Saginaw River Delta. Fine sediment is going to be carried further out because it takes less energy to transport that. And wind moves sand and finer sediments outward, or inward, I should say, to coastal dunes. Tectonic activity can uplift or downdrop a coast, and you can have changes in sea level from tides and other factors. These offshore currents, they move water, and they can affect sediment transport as well. So we got low tide, high tide, waves, faulting, uplifting a coast, and then wind activity. Okay. So the appearance of the shoreline, that can be affected by a lot of different factors. Much of our wave erosion occurs during storms. We can have steep shorelines allowing waves to break close to the shore. Let's see, the orientation of the shoreline relative to prevailing direction of waves is important. And then the availability of, different kinds of sediment, like from rivers, is important. And climate controls how much precipitation, vegetation, and what type of rain events we have. All right. So what are tides exactly? We don't have that so much here in the Great Lakes region. Tides are cyclic changes in the height of the sea surface. So high tide and low tide are about every 12 hours and 25 minutes. Okay, so you have high tide here versus average sea level. High tide floods more shoreline. Low tide exposes more land. And the water level doesn't just stop at the average sea level. It's always moving, right? What causes tides? So we can look at this diagram and note how the height of the sea surface, the blue edge, relates to the position of the moon. Okay, so right here we have the interaction of the Earth with the moon's gravity. And as we are close to the moon with the moon's gravity, we have this sea surface height rising. That's the blue edge. Okay, so we can note on the bottom figures where the tides are higher or lower. So if you have sea level here is higher relative to the moon and the sun, that's the new moon. And on the other side here, you have interaction with the moon's gravity at time 2, the full moon, or the quarter moon. Also influenced by the sun's gravity, causing sea level to be higher here. Now the moon orbits the Earth every 29 days. We've got mounds of water, but not water itself, staying aligned with the moon as the Earth rotates. And the Earth is rotating, say, beneath the mound of water. The mound is on the opposite side because the Earth is closer to and pulled more by the moon. Now the sun is larger, but it's further away, so it has less of an effect than the moon's gravity. And this is not to scale, by the way. They're shown as like way closer than they actually are. So each coastline rotates past each mound, say, once per day. Why are some tides higher than others? You can have a situation where you have more than normal and less than normal. All right, let's think about waves. How are waves described? You have a height, a crest, a trough, and then a wavelength between, say, 2 crests. Now, a wave moves through water, and the water moves much less than the wave. The water near the surface moves more than the water at depth. And below some depth, the wave base, the water does not move. The water itself moves in a circular motion with the wave. So you have like propagation of waves shown here. So second wave, first wave, wave base, under which there is no wave action. And we see with this direction of wave propagation, more movement towards the top, less, until you get down to the wave base where there's no wave action. That's the circular motion. So how do waves form? How do you think waves form, really? Waves can become larger with more wind, or they can die out over time. The wind blows across the water surface. As a wave nears the shoreline, it interacts with the bottom when the water depth is less than the wave base. So there's like friction that comes into play there from the floor, the sea floor, or the lake bottom. We also have gas molecules colliding with water to form those waves. And then waves can increase in size. If they become too steep, though, the waves will collapse. Okay, so just to show you with the shoreline, we have wave breaks where the wave base is equal to half of a wavelength. So again, how they interact with the shoreline. They can swirl away loose pieces of rock in this sort of reflective coast or break off new pieces. They can grind and break clasts or pieces of rock, making sand and stones that promote erosion. Now, waves can bend and refract if they approach the shoreline at an angle. And then the part of the wave that encounters the bottom slows, kind of bending the wave, and that's where you get a rip current. Pushes back out. Waves can break directly on this promontory surface from several sides. The bay here is probably going to be protected from most of the waves because they're hitting this surface instead. So, how does sand and other sediments get moved on a beach? You have movement of sand, see, with these waves. The waves wash sand and sediment back and forth near the beach. And during storms, waves carry sediment further up the beach, depositing it out of reach of non-storm waves. Now, storms can also erode material from the beach, leaving some beaches rocky during the winter months and sandy and less rocky during summer months. Sediment along beaches can slump downhill if the sea bottom is too deep, or too steep, if there's an earthquake or if sediment piles up too fast. And then finer particles of material can be transported long distances down coast by wind. Waves kind of approaching a coastline at an angle can transport sediment laterally along the coast, kind of like this. So what happens when a shoreline gains or loses sand with time? You can have sediment that's, originating largely from erosion on the land. Streams can also provide an influx of sediment. And then the dunes that we see along a beach, they are formed mostly from beach or streams, wave action. Now, or wind action, I should say. So beach erosion and slumping rocks can add sediment to the shore as well. You could have erosion of, say, coral reefs, which would add more material to the system. So the amount of sediment we have available to a system, we call that the sediment budget. And currents can also transport sediment along the coast, like this longshore current. Shoreline features are carved by erosion. We have sea cliffs here, caves and sea arches, pinnacles and sea stacks, and then wave cut platforms. You might also have a formation of a sea cave and a sea stack, and here's how that may happen. We have this promontory extending out into the sea. With enough wave action, we get a little sea cave forming underneath. Even more, we could have a collapsed roof of a cave and a formation of a sea stack. And then eventually the sea stack could be eroded away as well. This is progressive. Shoreline features formed by deposition rather than erosion include sandbars, depositing sand, a spit. You can see that along our local coastline. A barrier island, very common, say, in the Gulf Coast, where you get sediment deposited out in front of the continent. Now, Cape Cod is partially or partly a spit. A spit forms when waves and longshore currents transport sediment along a beach. So here's a little spit. A spit can become a bay mouth bar enclosing a bay, so like completely closed. And if you have sea level rising, the spits and bars can become barrier islands, which are always changing, constantly moving around. They're really cool to visit, but maybe building on them could be dangerous because it's a very dynamic area, right? What might happen if sea level rises relative to the land? Okay, so the land is going to be inundated by the sea. The hills can become islands. River valleys may flood, forming an estuary. And then dunes and other coastal features might become offshore bars. Barrier islands and other types of islands may be submerged. So a submergent coast includes the Chesapeake Bay over in Maryland, Delaware, DC area. This is the Chesapeake Bay estuary. The bay was a valley originally carved by rivers, but flooded when the sea level rose. Fjords are narrow, deep embayments, and remember we pointed to glaciers assisting with the formation of those. Same thing with these river valleys. Carved by glaciers and then later invaded by the sea in Norway. And barrier islands are interpreted to have formed by rising sea level, cutting through the barrier. What happens if sea level falls? So we have a reef and a sandbar on the left. Less sea level, you could get erosion and sizing into the beach and other land. Obviously, a lot more beach is going to exist, and we see this in the Great Lakes pretty often. More beach, less beach. You could have exposure through wind erosion of wave-cut notches and terraces. And the reefs as well may become exposed on land. Sandbars themselves can become coastal dunes. Some more characteristics of emergent coasts. We've got these wave-cut notches formed at sea level. They'll be above sea level, then SL. Then coral reefs are exposed when sea level drops or the land is uplifted by tectonics. And wave-cut platforms are now marine terraces high above sea level. How would each factor affect sea level? So glaciers are back. So an increase in glaciers equals a fall in sea level because we've got the water trapped up in the ice. Less glaciers equals a rise in sea level. Looking at tectonics and spreading rate. So slower seafloor spreading, that's going to equal narrow ridges like the mid-ocean ridge and a drop in sea level. Faster seafloor spreading equals broad ridges and a rise in sea level. And then ocean temperature. If the ocean cools, water contracts and we'll have a drop in sea level. Conversely, if we have warming oceans, we'll have a rise in sea level. And we sort of alluded to this, but The position of the continents on the planet influences global sea level. Ice sheets form on land, so that land must be at high latitudes near the poles for large ice sheets. That would be abundant glaciers, which result in a drop in sea level. So you would have less glaciers if the continents are at lower latitudes. Yes, and that would keep the sea levels high. So if the continents are towards the equator, sea levels would be high. So loading and unloading affect elevation. And I'm talking about loading in terms of ice loading the land. So the ice pushes down on land's surface and the seas inundate the region. When the ice melts, the weight is unloaded and then the region flexes back up. We call that isostatic rebound. Loading and unloading, they do affect a lot of our elevation. Rebounding is continuing for thousands of years after the ice is gone, and this is in Canada. Say over the last 2 million years, this has been a thing here. Okay, so waves are included in hazards along shorelines. Obviously, storm surge, strong winds, those are all hazards that we see. This is damage that we see from Hurricane Fran in 1996. The before photograph shows 2 different houses. The after photograph shows destruction of the houses caused by waves, storm surge, erosion, wind, all that. This hurricane came ashore with sustained winds of 185 kilometers per hour and a 4-meter high storm surge, and that's in Topsail Island of North Carolina. How do we approach shoreline problems? Well, we can put up a seawall or riprap. Riprap is a bunch of rocks in Michigan along a coastline. We use rock now. We used to use concrete, but now rock is the only way. You can use breakwaters, groins, whatever, to try to keep the storm surge from completely eroding away the coast. You can build a jetty out, like a long wall of rock. All this to stabilize the shoreline. You can only do so much because nature is bigger than us, really. So how do we study shorelines? We can measure the elevation of the land surface. We can look at low-lying areas as well, like river valleys. We can map the resistance of the bedrock to erosion. And we can map and measure coastal dunes. We can also assess the slope of the land and sea floor to see how steep it is, and document the width of beaches and the impact of constructed features that we put there to keep the beaches in place. We can also monitor the location and height of sandbars and barrier islands. So here's a barrier island, and we're looking at the hurricane-related changes to a barrier island. Okay, so this is an old image prior to the renaming. But this LiDAR data shows detailed elevations. So post Hurricane Ivan, we got a lot more smoothing. The lumps were the houses. Okay, they're still kind of there. The road is also visible in the first image. It is now gone because the sediment went over it. So I guess it could have been even more devastating, but it was in September 2005 after Hurricane Katrina. Oh my goodness. So you had so much of this barrier disappearing and homes as well. This is in Dauphin Island, Alabama. I have been there. What they do is just rebuild again and again and again. So think I was there in like 2013. Yeah, it looked pretty stable then, but it's constantly changing. So there are calculated changes caused by these storm surges along the coast. So these LiDAR data compare before and after elevations. The red means that material is lost, mostly houses. Green is gained, so that's redeposited sand. So we lost all these houses, but we gained sand back here. Okay? And a lot of this isn't even land anymore. You've got water. Water here. So barrier islands are constantly changing. They're dynamic, but they're beautiful, so we visit them and we build on them. That's the way it is. Okay, so we'll look at the setting of these glaciers, ice sheets, and ice shelves near West Antarctica. You have West Antarctica mostly covered by ice. The transantarctic mountains divide West Antarctica from East Antarctica. And West Antarctica contains 11% of the ice in Antarctica. The land is flanked by 3 large ice shelves, and the central part of West Antarctica contains an ice sheet as thick as 3,500 meters. The base of the ice sheet is below sea level. The central part of the ice sheet is resting on solid bedrock, and the outer parts are floating on the sea. So each ice shelf loses large volumes of ice every year by calving of icebergs and melting of the underside. The ice sheet builds on land and moves toward the sea. And the outer parts of the ice sheet float on the ice on the sea as an ice shelf. But what could happen to West Antarctica if global temperatures or sea levels rise? Well, we have part of the Larsen ice shelf collapsed in 2002. This is what it looked like before the collapse and then after the collapse. Now, warming could melt more ice, and rising sea levels could float more of the ice sheets. So one possible scenario would be rising sea level floats more of an ice sheet. It detaches it from the bedrock with a large fissure in the ice sheet, causing melting. So more collapse. And we'll stop there for today.